Okay, so first of all, I would like to thank the organizers for giving me the opportunity to show my work here. And the goal of my project is the fabrication and characterization of advanced nanosuperconductors in the 3 dimensions using an additive manufacturing technique based on focused ion beam technology. The motivation of this project is the study of novel physical phenomena that emerge when a size of a superconductor is reduced to the nanoscale in the range of its superconducting coherence length and penetration depth. For example, superconducting vortices have the potential to be used as a quantized information carriers that could be used in the design of nanocircuits, and moreover, superconductivity can be modulated using an electric field as an external stimulus. So these nanosuperconductors and devices could serve as a building blocks for the applications in quantum computing and nanoelectronics respectively. So if we add in a curvilinear and 3-dimensional geometry in these nanosuperconductors, unconventional physical phenomena could emerge in which geometry, chirality, and topology could be interlinking. So these materials may hold promise for emerging or future development of multifunctional technologies. However, as you will see during my talk, there is a lot of work to be done in which, well, their fabrication and characterization remains a huge challenge. So this is a general sketch of the additive manufacturing technique. This is called focused ion beam induced deposition. The precursor molecule that I use for the fabrication of nanosuperconductors is tungsten hexacarbonyl. And those molecules are delivered from this nozzle and absorbed at the surface of a substrate, and the focused ion beam is scanned over the surface, partially decomposing those precursor molecules, forming a deposit. So in 2004, Satie and co-workers reported that these tungsten carbon nanowires run using Ga+FIB presented superconducting properties below 5 Kelvin. It's a type 2 superconductor, S-wave, and the upper critical magnetic field was around 9.5 Tesla, and the superconducting coherent length around 6 nanometers. Later on, in my previous group in Zaragoza, we observed that this material follows properly the BC's theory, and moreover, we observed for the first time a direct thermally depending and melting transition of inner 2-dimensional vortices lattices. And what is happening when the size is reduced to the nanoscale, we observe a reentrance of the superconductivity as a function of the applied magnetic field in nanowires of 50 nanometers in lateral size due to a strong confinement of a single vortex row at the center of the nanowire. More recently, other authors have been reporting tungsten carbon nanostructures grown using the helium beam, and later on using a different precursor material. And it's possible also to grow niobium carbon microstructures using the gallium focused ion beam. The superconducting properties of those materials are comparable to the superconducting properties of tungsten carbon wires reported previously. So let me just to summarize some of the results regarding planar tungsten carbon nanosuperconductor and devices. And first of all, I would like just to mention that in 2018, Josephson's group reported that superconducting methods could be modulated, the superconductivity could be modulated as a function of an electric field. And they experienced those effects in titanium, vanadium, and for example, aluminum materials. And these effects allows them the opportunity to create different kind of field effect transistors as this Josephson interferometer or the ion-bridge field effect transistors. However, the mechanism behind this field effect is still very controversial. And in order to put some light in this physical mechanism and to see if this effect is extended to other superconductor materials which are not purely metals, we created such a kind of field effect device using our tungsten carbon material grown using focused ion beam induced deposition, using Ga+FIB and also using the helium beam. And we use the similar strategy that's used before by Josephson's group. This is a typical SEM image of one of our devices. It consists of 45 nanometers wide and 3.5 microns long nanowire, and the gate voltages are these two, and the separation between the gate voltage and the nanowire was around 70 nanometers. And as Josephson's group reported, we observed a modulation on the critical current as a function of the gate voltage at different temperatures. And we think that this effect is due to the squeezing of the supercurrent as a function of this electric field effect. And these experimental data are in good agreement with a simple theoretical model based on Ginzburg-Landau equation developed by our chairman, Vladimir Fomin. So we wanted to extend these devices in a different material, that one ground using the helium beam. In this case, we use it a wider wire, and even the separation between gate voltage is at least a bit higher compared with the previous device. And at the same way, we observe the same modulation in the critical current as a function of the gate voltage at different temperatures. And just having a look at the transconductance, that is a figure of merit of the performance of field effect transistors, we obtain a similar values comparable with the transconductance values obtained in other superconducting materials, but even using a lower critical gate voltage. And even taking into account the critical current, the critical temperature of our devices, in principle, the applicability of these devices is in a wider range of temperatures compared to the other superconductors. So a summary of this first part of my talk, if we obtain a local suppression of superconductivity induced by an electric field, we obtain this superconductivity modulation at really low values of the gate voltage, and this gate voltage is comparable with those used in MOSFET technology, and we develop a simple theoretical model in agreement with the experimental data. And of course, these kind of devices could serve as a building blocks for cubic superconducting field effect transistor devices, Josephson junctions, logic gates, and single photon detectors. So let's move to the second part of my talk regarding three-dimensional nanostructures ground using focusing beam induced deposition. In this case, I use a helium beam instead of the gallium beam, because the diameter of the helium beam allows you to create really nanostructures. That is not the case when we are using the Ga+FIB. And I will just to emphasize, comparing with different techniques used for the fabrication of 3D nano objects, that focused ion beam induced deposition is very flexible in terms of shape and 3D geometry, as you can see here, and also regarding the resolution that you can achieve, that is in the range of the nanoscale. So you want to create real three-dimensional nanostructures with really high flexibility in shape and 3D geometry, the technique is focused ion beam induced deposition. So in this case, we can just find two examples of 3D superconducting nanostructures ground using Ga+FIB. The first one was reported in 2010, some time ago, tungsten carbon wires, but as you can see in the SEM image, the resolution is pretty pure. I mean, the diameter of the wire is around 250 nanometers. Although the superconducting properties of these materials is comparable to the superconducting properties observed in planar structures. And in the case of niobium carbon nanowires, we had the same problem regarding the resolution, that is around 250 nanometers in lateral size. And also we observed that the superconducting transition is not so sharp as we would like to have it. And also in some devices, the resistance is not dropping to zero. So it seems clear that there's a lot of work to be done in order to improve the quality of the superconducting 3D superconducting nanostructures and in the for improving the superconducting properties. So I'm going to summarize some work already reported in different papers regarding 3D superconductors using the helium beam in order to get really nano-superconductors and devices. And the first example is the fabrication of hollow nanocylinders, and it's a very simple way to do it. and is the precursor molecules that absorb on the substrate, and the helium beam stays at the same position for the deposition time, producing two effects. The first effect is the growth of this nanocylinder. At the same time, the helium beam is producing a hole, a cavity at the center of the nanowire due to the helium beam milling. So it's just using that very simple way, you can create such a kind of hollow nanocylinders of 32 nanometers in outer diameter and around 6 nanometers in inner diameter, and the aspect ratio was around 200. So it's something that we cannot create by using a completely different nanolithography technique. So it's a really huge advantage. So what can we do? We can tune also the diameter of these hollow nanocylinders, just modifying the ion beam current. The ion beam current correlates with the ion beam spot, so we can just increase the size of the outer and inner diameters, just increasing the ion beam current. And in that way, we can control the 3D dimensions of these hollow nanowires. And here, interestingly, you can see in this 3D tomographic reconstruction how the cavity, the hole in these nanocylinders is starting from the top part and finishing at the bottom part. So with that, we can be demonstrating that we are able to create these hollow nanocylinders with at-will dimensions like hollow nanowires. So regarding the composition and microstructure of this material, we obtained that the grain size is around 20, 30 nanometers, and the crystallographic structure is compatible with the tungsten carbide FCC structure, and the atomic percentage of tungsten was around 72%. That if you have a look at this small box, those values are really good and better regarding the crystallinity and the higher tungsten content compared with tungsten carbon wires grown using the Ga+FIB. So regarding the superconducting properties, we observed that those materials are superconducting as well, and the critical temperature is higher than those reported using the Ga+FIB. And regarding the upper critical magnetic field, it's almost similar. The upper critical magnetic field is higher. So just using this very simple strategy, we are able to grow 3D hollow tungsten carbon nanocylinders using the helium beam with better resolution, higher aspect ratio, higher crystallinity, higher purity, and improved superconducting properties. So let's move into the second example of the 3D tungsten carbon nanohelices. We can see that just modifying two deposition parameters, that is not really complex, I'm able to tune the nanohelix diameter and the turn length of pitch between them. So just modifying these two parameters, I'm able to grow nanohelices with at-will three-dimensional geometry. And here I show you a few examples. I was trying to keep constant the diameter of the nanohelix around 100 nanometers, and the turn length is from 200 nanometers to 1 micron. And in the other way, 200 nanometers in diameter or 300 nanometers, and the turn length is from 400 nanometers to 2.3 microns. So it's possible to really tune the 3D geometry and the distance and the diameter between each turn and the nanohelix diameter as well. And the wire diameter is around 50 nanometers, the wire diameter of each nanohelix. Regarding the superconducting properties, I selected these 4 nanohelices in which I can compare with the same diameter, the smaller one, 100 nanometers at different turn length, and another diameter of nanohelix around 300 with different turn lengths. And I studied those superconducting properties using magnetotransport techniques, and I obtained very similar superconducting properties in all of these nanohelices in terms of the superconducting temperature, the critical temperature, the upper critical magnetic field, and even the critical current density that I was not showing here. So this is giving us an idea about the robustness of the superconducting properties of nanohelices with completely different 3D geometry. And interestingly, we observe a completely different behavior in one type of the nanohelix, in that one, and we observe here how the resistance as a function of the current is related at different jumps in the resistance, which are related to the occurrence of phase slips as supported by numerical simulations based on time dependence Ginzburg-Landau equation, which is a collaboration with the Professor Fomin as well. And here we can see in the point number 4, for example, how the vortices patterns are inside of the nanowire, and in some moment when you are increasing the current, two large regions of phase slips were introduced into the patterns, producing that large jump in the value of the resistance. And in the second point, is happening almost a similar way. Two more regions of phase slips are inserted in the wire, and we observe again a second jump in the values of the resistance. So this is a demonstration of a proof that this three-dimensional geometry could tune the superconductive properties of these nanohelices, because of course this is not visible in planar stratas with the same dimensions. And well, the summary of this second part of my talk is that we were able to grow individual superconducting hollow nanoscylinders and nanohelices with really small diameter and high aspect ratio. And this helical 3D geometry give us fingerprints of vortex and phase slip patterns experimentally identified and supported by numerical simulations based on time dependence Ginzburg-Landau equation. And let me just to finish thank people involved in those works and the financial support of different agencies. And of course, thank you very much for your attention.
Thank you very much, Rosa, for a nice presentation. So,
on the first part of your talk, you showed this switching field, switching voltage, right? At 6 volts, which is much less than the previous ones reported. What's in terms of the field?
In the term of electric field,
yeah.
I have not these values in mind, but I'm pretty sure that this difference in the gate voltage is mainly because there are not metallic superconductors.
Oh.
And that's why the reduced value of the critical gate voltage that we need to apply to
so this also leads me to the second question. So do you think there will be some peculiar materials? I mean, so they should be more metallic, these superconductors,
well,
with low resistance, for example, I don't know.
Yes, but in that case, for example, the metallic superconductors, at the end is you need to apply really huge electric field.
So the contrary, yes, the opposite, I mean,
exactly.
Yeah, okay.
And then is, for example, there's one example based on instead of carbon nitrides, superconductors, that they are not also too much metallic as well, and they obtain well, in the range of less than 10 volts of gate voltage to observe a modification or modulation of the critical current. But in that case, they induce higher values of the critical current instead of decreasing the critical current.
Okay.
But they were applying a back gate voltage that is not exactly the same as in this case. Then it's difficult to compare those different devices.
Okay, so you're feeling it's more resistive, it's better. Okay, thank you.
Yes, well, semiconducting, you know, yeah.
Concerning that first part, I mean, the controversy with the results from Chiasotto is actually the leakage current.
I know
so
it.
Did you mention that?
Yes, exactly. Yes, I was introducing the gate voltage using a Keithley, and the same moment that you can just tune exactly what is happening. I mean, you introducing voltage and measuring the current, and the values of the current that they measure were negligible compared to the critical current that the current that I'm introducing in the bias system.
Okay.
So one of the ideas is just to try to, increase the separation between the gate voltage and even decrease the lateral size of the gate electrodes, just to confirm and to see that there are not any kind of relation between this leakage, or at least, I mean, normally there is a leakage in any field effect transistor.
Right? You didn't show
No.
the leakage. Because I mean, we tried to do something similar, but it's always leakage.
Okay.
Yeah, can I comment on that? So I appreciate you say it's a controversy, but indeed I also really agree with you with your suggestion. And for me, it sounds like strange. It's not has been done. Is to do scaling with the size, because because we together with Alejandro with similar experiments and saying there is no leakage current for me is like how many current you need. A single electron with an electron volt will be enough, and your Keatley will not detect that. So I think.
Yeah.
I fully agree with you. We should do the scaling and see that the voltage scales, and that would be right. Finally, stop the controversy. I think.
Yeah, no, I fully agree, because it's something that it's clear that there are some parts that it's just energetic electrons that are trigger the large amount of quasi-particles that drive back the superconducting to the normal state, and it's clear that it's very important to know exactly what is the mechanism behind of this field effect to know how to solve this kind of problem, because leakage in a field effect transistor is also one of the problems for the performance of such a kind of devices.
Yeah, but then I think your technique is really powerful to solve this question. So that's what I want to say. It's a positive thing. I would say this is perfect for tackling that question once and for all, and to get rid of this controversy, I would say. Thank you.
You're welcome.